Good morning, everyone. I, Amita, on behalf of NASSCOM, welcome you all to the ninth edition of NASSCOM Annual Technology Conference. Let's begin with our first workshop, Bayesian Reasoning and Modeling in Machine Learning by Anurag Sahay, CTO and Global Business Unit Head, AI and Data Science at Nagarro. The last few years has seen a lot of momentum in Bayesian approach to statistical thinking and reasoning. Bayesian approaches are a powerful set of thinking tools to help us solve situations where uncertainty takes a center stage. In this workshop, Anurag will deep dive on logic of uncertainty and how do we measure it, key ideas and what do they mean, how do we use these tools to solve practical problems for everyday life. Let's welcome Anurag. Over to you, Anurag. Over to you, Anurag.
Thank you, Amita. It's a pleasure to be here. Let me quickly share my screen and then move on to the presentation. So, hello everybody. My name is Anurag, and I am going to take this session today. I am I'm leading the data science and AI practice at Nagarro, and in my role as a leader in data science and AI, I work with several practices where we work with different data sciences and AI technologies, and try to use them in efficient, powerful ways to try and bring solutions for our customers. Now, there's a lot of very interesting set of problems that we get a chance to work in, and just like any skilled person, we would want a repository of tools in our toolbox to be able to take them out for solving the most appropriate problem with the most appropriate tools. Now, in the last few days, years, machine learning has been one of those very popular tools that a lot of people have, a lot of data scientists use for solving many different types of problems. But along with machine learning, there are some very interesting and effective methodologies that have also come about to think about solving these problems for different contexts. One of them is Bayesian modeling and Bayesian statistics in general. Interestingly, if I was to just spend a few minutes around the background of statistics and Bayesian statistics in particular and why it's important, because we, again, for various reasons, machine learning gets a lot of attention and some of these other things don't. There is, as far as data scientists go, a lot of people approach data science from a programming first approach, which is, to approach it from a programming centric way of solving problems. Statistics, on the other hand, is more of a thinking kind of a tool, or at least gives frameworks to be able to think through problems in many different ways. To be able to build up a problem from the first principles is very powerful. Whether you use frequentist statistics or you use Bayesian statistics, generally, period. I mean, if the fact that you're using statistics to frame a problem, it's a very efficient way to think about, and also a very powerful way to think and reason about what problems are going and how the problems are going to be solved and so on. Statistics is one of those stepchildren that gets ignored at some level. And we often encourage a lot of our data scientists in our org to start focusing, while they're working a lot with machine learning, to also focus on statistics. And when it comes to statistics, I mean, a lot of work that we do, we see value in this new paradigm that's coming about, which is Bayesian statistics. So think about the way we think about data science is that a data science definitely programming first approach, a machine learning first approach, and all of that goes with that. But at the same time, it needs to have a thinking first approach as well, and that's where statistics and primarily Bayesian statistics comes into play. And in my presentation today, I'm going to talk a little bit around Bayesian statistics, and try and walk you through the different ways we think about Bayesian statistics and work with them, and try and model them and so on. So that's the topic, and I'll explore the topic a little bit more in detail as I walk through the different slides. I want to talk about three important things with Bayesian in the Bayesian paradigm today. First of all, I'm going to spend a lot of time framing the Bayesian methodology, which I sort of call thinking about the problem. Again, in my view of the world of data science, there's just not enough thinkers in when it comes to this paradigm. Again, it gets, the focus moves too quickly, too early, and too quickly on programming. The second important part is modeling. So once you've thought through a problem, you would want to model it. And that's where, a mathematical model comes into play, a programming model can come into play. And then, of course, once you have modeled it, you have to make sensible inferences from what the model that has been drawn. Again, if you were to draw parallels with machine learning, the inferencing stage is sort of replaced by prediction at some level. And a lot of folks, when they think about machine learning problems, tend to very quickly go into classification or regression, and it's either a prediction of a yes or a no, or whatever the regression value is. Whereas inferencing is also a very important set of activities which gets ignored with the machine learning framing, so to speak. So I'm going to talk about all these three important ideas: thinking, modeling, and inferencing, and I'm going to root all of that in the context of Bayesian statistics. So let's start with a small story to sort of get ourselves going. And this is also a very important idea, which I'll hopefully circle back at some point. Let's say that you are, sleeping in your bedroom one night, and you're sort of looking out of the window of your bedroom. And at that instant, you sort of see a brightly lit, sort of saucery shaped object move into the sky through your window. You're like sitting there watching all of that. And the moment you see that, you would react in a certain manner. Of course, you would see, you might sit up on the bed, you might rush to the window and try and peek in, because that brightly lit rotating saucer like thing seems very interesting. It's not something that you've sort of seen before. And what is happening is, in that little split window, is that you are going through a whole Bayesian reasoning cycle. And I want to explain what's going to happen there. And so this is a story, of course. So I have freedom here to describe and decide it in the way that could lend credence to the direction that I want us to think through. You Before you jump to the window, you have a certain view of the world. You already have it in your head. You know that flying saucers are not very common in this world. Actually, not at all common. So you think of, when vehicles move, they move on roads. Planes move, but planes don't move in rotating or circular orbits. So there is a certain view of what you already think how this world behaves. This is your starting point. You're not starting from scratch. It's not like you have no view of the world. You have a prior view of the world. I choose to call it is that you have a certain experience of how the world is. Now, that was already there before you even started looking out of the window. But then you saw the flying object. And that's the thing that you see. You made an observation. You made the observation that there is a flying saucer-like object that you can see from the window. And in that split second, you formed a hypothesis. You don't know about it. You don't know unless you're super aware, but you have formed a quick hypothesis. And I'll talk about what that hypothesis is you might have formed. You might or might not evaluate that hypothesis. You might just accept it as a given, like, oh, in this world, anything can happen. You are a person with that sort of disposition, or you might be a person with a disposition saying, well, how can that happen? Right. And when the moment you say that, how can that happen, there's a surprise element in what you're seeing. You're not expecting that hypothesis to be there. But nevertheless, there is a quick hypothesis that gets formed and it might or it might not get evaluated. And then there is a update to your total view of the world. You are no longer holding the same view of the world as you were before you saw the flying saucer. Now, all this happens very, very quickly. It is not something that you will have any time to deliberate through. But as data scientists, as people working in these problems, we want to look at that split second and break it into the four steps that I just described, and we work and we try and form a workflow about what's really going on, and then try and model it in some sensible way. So that's the story. um, and let me try and start framing it into a simple way that I would describe it using some kind of maths. So I have the word p, which is probability, and then I have something of a bracket, and I describe it in a very simple English language. I say I see a bright light outside the window, and I see a saucer shaped object in the sky. Now, that's me talking and describing it in English, but I write it in a very interesting way because I'm trying to write it in a mathematical symbol. I'm saying bright light outside window, comma, saucer shaped object in the sky. And the way I'm reading that is bright light outside the window and a saucer shaped object in the sky. So the comma is representing and at some level. And then there is a vertical bar. And then I say, given the experience on Earth, the probability of this whole thing is very low. And I'm expressing surprise here. What is the level of surprise I have in what I just saw right now? So the whole thing can be read as that the probability of observing bright lights and a saucer-shaped object in the sky, given our experience on Earth, is very, very low. Now, this is an important step because eventually I would want us to think about mathematics and then modeling and then inferencing. So it's important that whatever we do, whatever we have gone through in our heads, we want to sort of model it somewhere. Now, we obviously don't want to write this whole English language kind of thing every time we want to do something. So, mathematics is also about representing a lot of those ideas in the form of variables or symbols. So I replace this whole idea or a concept of bright light outside window and saucer shaped object in sky by this thing called D. You can think of it as a symbol. You can think of it as a variable that can take a value, right? And then I also replace the whole thing about this whole thing about I have a certain experience on Earth with another symbol called X. And now this whole equation itself can be written as in a much more concise, readable form of probability of D given X is very low. So I'm starting from very basic areas. A lot of this is obviously very common, but still, the translation from language to maths is super important when we think about things like Bayesian statistics and so on. So what's really happening is that if I was to again go back to my idea of what were the four steps that I followed through, um, the if I was to take the place from between this, I saw this observation to this third, the final state about your update of the experience of the world, and ignore this thing around experience of the world, but just start from the second step all the way to the fourth step. So I'm going to describe, this is what I'm trying to describe here. So we made an observation. Anytime you make an observation, the scientist in us, it craves for an explanation for that observation. Like, where is that? How do you fit what you just saw with what you know already? And so that's the step of explanations, right? And so all observations, they necessitate explanations. Now, when we look at explanations, based on explanations for our view of the world, we inspire a hypothesis. We say, we make a certain claim about why that observation would have come through. So it's coming through because I have a certain view of the world, which is the explanation. And then I'm using that view of the world to propose a hypothesis that can explain the observation. And now, once I have that, and I have an assessment whether that hypothesis is true or not, I can then, assuming that, let's say, my hypothesis is true, I can make even a further prediction. So the step between observing something to modeling something to eventually predicting something actually breaks into these two super critical steps called explaining and hypothesizing. Again, things which we ignore as machine learning practitioners, but something like a statistics oriented thinker would very naturally do, to be able to move from, from the place of observation to a prediction. So again, let's deconstruct that a little bit in this view of the world, like what we just saw. So we saw a brightly lit up saucer like object in the sky. That was the observation. The explanation is it could be a UFO, or somebody can come up with a better explanation, and the explanation could be a theory that there are multiple uh, life is there is life in this universe above and beyond this planet. That could be a better explanation. It could be a theory. Now, if that was the explanation, that there is life beyond this planet, then it's very normal for us to propose the hypothesis that there could be UFOs. So you have to believe in the theory first that there could be life outside this planet before you can propose the hypothesis that there are UFOs, for example. And then, if you come up with this explanation that there are UFOs, this hypothesis that there are UFOs, then you can sort of make all kinds of predictions. You could say we could make an alien contact in the next few years. You could say, what if, and this prediction doesn't fit this whole thing, this framework here, but I just put it there because there could be another explanation. The explanation could be, for example, that there are there is secret technology that some countries have that's very powerful. The hypothesis in that case also could be that there are UFOs, but it's coming from a different explanation. And in which case, the prediction would be different. The prediction would be some countries have been able to build an UFO. So these four steps, and more importantly, the explanation and the hypothesis steps, are super critical, because this is where the thinking is really happening. And the whole trick is in being able to come up with a very good explanatory model, and then come up with very specific and relevant hypothesis to be able to describe the observations that one is seeing. And if one comes up with a good view and a hypothesis here, then one can really come up with very interesting predictions, which can actually further knowledge in some very interesting ways. So that's the general framework, that is what I'm trying to propose to you all as a thinking exercise, and I'm going to spend some more time on describing this a little bit further before we go into the modeling bit of our presentation today. So let's look at that into one level deeper. So when we have our data D, which is also the observation that we have seen a bright light in a saucer-shaped object, and a prior experience X, we can't ignore the prior experience, so we have to keep that along. In order to explain what you just saw, you need to form some kind of an explanation and some kind of a hypothesis. So that's together is the model that the world, that you're making. And that model is going to help you make a prediction. So predictions don't come from just some vacuum space. They come from a view of the world and an hypothesis. And that's the thing to really be very clear about when you're working with data science problems. Now, there are very important beliefs about the world that come, and they all take the shape of some hypothesis. So, for example, a scientist, they may hypothesize that a certain treatment will slow the growth of cancer. Now, where is the scientist getting this hypothesis from? It's because they have an understanding of what cancer is, and why cancer comes about. And because they know that, they can use that as a way to build, as a worldview from which they can then do some computations or thinking to propose a hypothesis saying doing this specific thing will slow the growth of cancer. So, although I'm proposing the hypothesis, what I also want to draw your attention to is that there is a worldview behind that hypothesis, the explanatory bit. A quant, for example, in finance, what we typically call, a quant or a quantitative analyst, they have a view of how markets behave. How do you think of markets? And then based on that, they can come up with very specific hypotheses about why interest rates will rise in the next 5 years, because of the view that they might have. And that might be a hypothesis to explain a whole bunch of observations that they might be seeing about the economics of a country at the present moment. A deep neural network can predict images, which are, which images are animals and which ones are plants. And where is the neural network building that idea? When given, an image, how does it come up with an animal or a plant as the prediction? Deeper down, although it's not the same as we making an explanatory view and hypothesis, there is some construct of, like, this is all how animals look like, and this is how all plants look like, because we have, in the training data set, created enough of a view of what might be the common set of things between animals and what might be the common things amongst plants. And then when a new image comes by, it tries to use its understanding in a form of a hypothesis to predict which ones are animals and which ones are plants. Now, neural networks are slightly harder because there is no tangible explanatory view or worldview and no clear hypothesis. It seems that they're both the same. And I have difficulty always differentiating between those two. But when we're thinking of cognitive models that people have to be able to explain things, then you can sort of separate explanations and hypothesis much more clearly. Then, once you have an hypothesis, you have to connect it with predictions. So again, the explanatory view, the hypothesis, and the prediction. Um, just like I described some slides before. So if you believe that the Earth rotates, then you can predict that the sun will rise at a certain time. Even if you did not watch or have any data, you could use this. You can use this model because it's a fairly simple model, and we know enough physics to sort of say that if something is rotating, it's going to, that point or that face is going to come again in front, and so whatever you're looking at, it will come again and then disappear and come again and disappear. So you don't even need data for making a prediction like that. You can just use the physics to make that prediction. If you believe that your favorite basketball team is the best, you can predict that what are the chances that they will win more games than the other teams. The favorite word here really doesn't matter. What I'm basically saying is that if you have a view of which teams are good and which teams are not, then you can use that knowledge to be able to say something about the future. And the same thing with astrology. So just circling back to this idea, right? And this is where I think it's super important that we sort of keep that in mind as a thinking framework, is that when you see an observation, you want to come up with two things. You want to come up with a underlying theory for where is that observation might be coming from, and then you want to propose a very specific hypothesis to explain the observation. And if you do these two things well, then what you have is a very powerful prediction machine that can help solve the problem. So that's what I was trying to illustrate. Now let's make it a little bit more quantified at some level. So when you see the evidence, you think you're seeing a UFO, you're forming a hypothesis. We've already talked about this. Now, we will represent that hypothesis with a symbol H1, and that sort of represents the idea that there's a UFO in my backyard. Now, look at this last statement that I've written, right? And that's what I want you all to think about. And this is super important because that's the whole purpose of a hypothesis. what I'm writing here is that the probability that I've seen this observation, sorry, so let's not look at the left one first. Let's look at the right one first, because that's sort of easier and then we'll parse it better. The probability that I'm seeing a brightly lit object and a saucer shaped object in the sky, given our experience on the Earth, is not as um, is more surprising than if I was to sort of look at it in the context of that the probability that I'd see that brightly lit object and the saucer shaped object even in the sky, given the fact that I know that that there are UFOs and what I'm seeing is a UFO. So proposing a hypothesis that there is a UFO is a higher chance of, that what I'm seeing can be explained better from that than what can be explained given just my experience on the Earth. And so adding this H1 or adding this hypothesis actually improves the probability calculation, the surprise calculation that I'm trying to do at some level. And here I'm only doing a comparison between these two surprises. Like, which is more surprising? The fact that I'm seeing something, given that I already have, whatever experience I have on Earth, or the fact that I am seeing something, given that I have a certain experience of what and how things are on Earth, but also given the fact that there are UFOs in this planet or on this planet. So a hypothesis explains better what we are seeing than without it. And then that's the whole purpose of making sure that one comes up with very interesting and specific hypotheses. So again, just describing that in English, which I always think is a very useful way to understand things, is that the probability of seeing bright lights and saucer shaped object in the sky, given my belief that this is a UFO and my prior experience, is much higher, and that's what's indicated by these double arrows, than just seeing bright lights and saucer shaped object in the sky without explanation. And so this is the justification for hypotheses. Unfortunately, again, as machine learning practitioners, I just do not see such activities, thinking exercises being done actively by that data science community. And I see a lot of statisticians very naturally gravitate towards hypotheses and explanations quickly, as opposed to machine learning practitioners. And this is where we try and do the balancing act when we are solving problems, the different types of problems, especially when it comes to domain, when you bring domain knowledge into the bit, right? When you're solving problems in marketing or sales or supply chain, it's really important that one knows the mechanics of what goes on in that domain, because when you understand that, you understand the hypotheses that can be legitimately formulated in that domain. And those hypotheses are the ones that actually lend more credibility, strengthen the probability argument, and then help you build models that can actually make sensible predictions, as opposed to just throwing all of that into a model somehow, whichever is your model of choice, whether that's a decision tree or a random forest or an XGBoost, and then just hoping that all you really care about is a prediction, completely bypassing the explanation and the hypothesis step. So it's this computing this probability of, something given something, that is the big question. And this is where Bayes' theorem comes in. Actually, the whole thing around Bayesian thinking, I mean, a lot of people just get stuck on the Bayesian formula, but the Bayesian formula is just a nice, neat way to calculate this sort of a complex probability equation, something called conditional probability, and it gives a very simple way to, calculate that. Although it's not that simple, and I'll just describe why is that not so simple. So here, for example, if we just parse this, what we have is basically the probability of a hypothesis being true given a certain evidence. E is here representing evidence or observation, right? So what we really want to say is that what's the probability that a hypothesis is true given the evidence? That is equivalent to the probability of that hypothesis being true, which is what is also sometimes called a prior, the probability of seeing the evidence if the hypothesis is true, right? And then the probability of observing the evidence. So these are the four terms. The probability of H, which is the probability of hypothesis is true, is also called a prior. So it's actually not the probability of data. So every time this is a confusing point for a lot of people, and I often encounter this in our conversations with our folks, is that sometimes people think, oh, prior is basically just the original probability of data. It's not. It's actually the probability of a hypothesis. This is also called likelihood. The probability that you will see the evidence given that hypothesis is true. So what we're really trying to say is, what's the likelihood that you would see that evidence given that hypothesis is true? Then a probability of evidence is the chances of seeing that observation in absolute. Like, what is the chance I would even see this observation? That's probability of E. And what you're really interested in is calculating is, hey, what are the chances that my hypothesis is true given that I have seen this evidence? Right? And that's what you want to strengthen and update. So if you look at it from another perspective, and there are some very interesting ways people parse it. Sometimes people parse it as hypothesis as a story, and so they say the probability of a story being true, given whatever you're observing, is the probability of the likelihood, which is the data or the of what you're observing, given the story is true. So had the story been true, what is the chance that you would see the data? Into what are the chances of the story being true, and then the probability of data. Now, this is all good. The denominator term is a super complex idea. What is the chances of seeing that data in absolute? And this is where anytime you use a Bayesian formula, if it's simple with simple situations, like if you're working with marbles and coin tosses and all the textbook problems, it's possible to look at all the possibilities of how data can be observed. Like if I have a box of like red marbles and white marbles, and I try and formulate a hypothesis there, I already know, like, what are the chances of the total possibilities, because there are only two kinds of marbles. But in reality, when I'm looking at any real world problem, the formulating that problem into a situation where I try and calculate the estimates of the total data is way higher, or way more complex. And so computing that is always a problem. It's always an integration. And this is also a segue to sort of, for me to try and take you into a place like, how do you use some powerful probabilistic programming approaches to be able to make this estimation. So let me try and take you to that. If I just quickly go and bring that. Second, where did that go? Right here. Hopefully you all can see my screen. It's not a problem. I'm showing you a Jupyter notebook. Do let me know, because I'm sort of blind here, not able to see if people are writing something on the screen. My screen is completely taken over by what I'm showing you all, but perhaps somebody can speak up in case they can't. Uh, you all can't see my Jupyter notebook, but you should be seeing a Jupyter notebook, and I'm going to walk you through some interesting ideas of integration. So all that I just described is the thinking process. Like I promised, I want to move to the modeling bit a little, and then the inferencing bit. Now, for us to be able to model things, computation is a very powerful ally, and we need to be able to think about how to model things using computation. I'm going to use obviously Python, and I'm going to use a programming language called PyMC. Now, PyMC is a probabilistic programming language. It's slightly different from other programming languages, whether that's TensorFlow or PyTorch. It uses its own infrastructure. It uses Asara and Theano, which are computation engines on which it has been built. I personally find it a pretty powerful paradigm, but you can do the same thing with other frameworks as well. There is TensorFlow probability, there's Stan. There are many other programming frameworks that can be used to solve a problem, and it's not specific to PyMC. But I'm going to use PyMC because that's what I know. And but the ideas that are discussed in PyMC can be applied in other languages as well. All of them, or the syntax will be different. So let me walk you through what I'm trying to show you. The problem that I'm going to try and show you is that how do you use computation to solve complex arithmetic problems? One of them is what is called Monte Carlo, Markov chain Monte Carlo methods. And I want to show you what that idea is before I take you to deeper into solving a problem using Bayesian probabilistic programming. So I've done the few steps around importing libraries, IMC, NumPy. There's a library called RViz, which helps for visualizing, Matplotlib, and then just I'm setting up a template for the plotting functions so that the plotting functions are sensible. In this cell, I am setting up a seed and then building a random number generator using NumPy. So you can set up a random number generator, and now you have a way to generate random numbers. Now, this is important because we are simulating a situation which is all about random variables and so forth. So what I'm going to do is I'm going to try and create 5,000 samples from a uniform distribution. A uniform distribution is a distribution where the chances of me picking up any point in that space is equally likely. So if I have points between -1 and 1, the chance of me picking any point is sort of equal to any other point in that space. And I'm going to choose a two-dimensional space, x and y. So hence the two and the n, which is the number of samples. So that's what I do. I generate x and y, and then what I do is I go ahead and plot that x and y. So I set up a matplotlib, PLT subplots. I'm just setting up some context. Then I scatter x and y, so they get scattered over this. I just make sure that the uh, endpoints are -1, 1 that are clearly visible. And because this is a uniform distribution, when you look at this whole thing, you can sort of see sort of equal, density being equal more or less across that whole space. Now, let's say I write a small equation, um, x squared plus y squared is less than 1. This is an inequality. So this whole thing will take a value of either true or false because there is an operator of less than 1. So either when I pick a value, give this function a value of x and y, it's going to return to me either true or false, right? Those are the two things that will happen. So I again plot, the same thing. I'm making a plot, and then I am taking the axis and setting up x and y values in a particular way. So I'm saying plot all those x values which are not in circle, meaning don't where the value returns false, and y where y is not in circle. So x and y are not in circle in this a certain x and y which do not satisfy this inequality, take that point and color it with C1 and the size of 1. And then the same thing, but this time the opposite. I say, take all the xy points which are true in the circle, meaning that they are in the circle, and then color them with C2. And then what you have is basic, and then I have another line which basically helps me plot this circular line around it, right? And so now what I have is, all the points which are inside the circle are green, and all the points outside the circle are orange. Now I'll just explain why I'm doing that. I want to do this so that I can, using just a random sample, calculate something very interesting. And here is the equation. The equation that I'm trying to calculate is pi r squared upon s squared. Now, what is pi r squared? That's the area of the circle. S squared, which is the side of the square. S squared is the side of is the area of the square. So what I'm saying is that the ratio of the area of the circle to the area of the square is equal to the random points inside the circle divided by the total points inside the square. So once again, I am equating two sides of the equation. The area of a circle divided by the area of the square, am making a claim that this is equal to the points inside the circle divided by the points inside the whole square. That includes the points inside the circle. And I'm choosing randomly, so I expect that proportion to hold. And when I think about that and I try and actually do this, I have actually putting the points inside the circle in circle dot sum divided by n. So pi is equal to 4 into points inside circle divided by total points, which is this equation. I actually get a value of pi equals 3.1488. And you can see that this is actually the case. This is the value of pi, very close to the true value of pi, uh, up to the significant digits that we can calculate. So what did I just do? I used some sampling computation approach to solve a mathematical equation. And this is what I want to show you all. What I'm trying to do here is to show you is that when we are trying to calculate the denominator here in this equation, it's a complex integration. And that's why one needs to have a good programming methodology and constructs to be able to calculate this integration in a sensible way. And this is where probabilistic programming framework becomes super important, because they have all these algorithms. They have an algorithm called Metropolis, MCMC, and NUTS, and many others, which are very efficient ways for us to make this calculation. And that's what helps us to do and solve a Bayes problem completely. So together with the idea of Bayes problem, combining it with the mathematics of how does one do complex integrations and complex calculations using random variables and sampling, combining those two ideas, we get into actually a framework where we can use this to solve different problems around Bayesian modeling. So let's go a little deeper and work this with an actual example. And let me work with a simple problem. This comes from this beautiful book. This example I'm taking from is from a beautiful book that I would recommend to all of you. It's called Bayesian Methods for Hackers, and it's by uh, Cam Davidson. You'd find it on the PyMC link, and it's a beautiful book if you go through it patiently and slowly. Pretty much every point that I'm describing here would be explained in much more detail, and you'll get the hang of how Bayesian thinking can actually be converted into a modeling exercise and then to an inferencing exercise. So here is a problem statement. These are the, as it's described here, counts of text messages received by a person over a few days. So approximately 75 days. So we're talking about 2.5 months. This person received different messages on their phone on any given day. The question that is being asked is, given this data, can you tell if the person's texting habits have changed over time? Like, is the person receiving more messages? If you think of receiving as the idea that this person is receiving more messages than they were before, in any is there a clear point in time that you can tell whether that person's habit has changed? So over the last, over the 75 days, at what point would you say that this person's habit has changed? Now, if you just eyeball that, you sort of feel like, somewhere here, you see the spikes here and so on, but you can't be sure. And this is just like gut feel. Visual inspection is really very hard to, use in a very powerful way to make final conclusions. You have to have some sensible way of being able to answer that question. So I'm going to walk you through a Bayesian programming idea now to try and deconstruct that a little. So let's say CI represents the count of messages that a person receives on the ith day. I want to hypothesize that that person is receiving those messages in a distribution which is Poisson. And if I think about Poisson distribution, right? Poisson distribution is basically a distribution that comes about from situations or events where if all the events are independent and I'm counting how many times something has happened in a given unit time. So if I'm like waiting at a bus stand and I'm like looking at how many buses cross me in every 5 minute window. Now, no buses are independent of each other. Let's assume that no two buses are trying to coordinate their time, and so buses are just working, moving and doing what they are doing. And I'm standing at a bus stand, and I'm just counting how many buses cross me every 5 minutes. And if I was to measure, calculate, count all that data, and I make a plot, what I would get is what is called a Poisson distribution. So mathematicians have already come up with a name for such a distribution. They've described the properties of that distribution, and one of the important parameters of the distribution is lambda, which is the mean value of how many counts on an average would you receive in given such a situation. So one of the important hypotheses I'm going to propose to myself, and remember, this is a hypothesis because I have to propose hypotheses to be able to solve a Poisson, to be able to solve a Bayesian problem. I'm saying that the count is basically a Poisson distribution with a certain distribution lambda, with a certain average value called lambda. And because there's a change in behavior of that person, I am going to say that the mean value is going to change on a certain day. And that certain day is maybe tau. I don't know. I have a symbol for that date. And I say if t is less than tau, then the mean was lambda 1. And if t is greater than tau, meaning, we are looking at days past that, then the mean is lambda 2. So I'm sort of making that supposition. Now, lambda 1, lambda 2 themselves have to be something of a parameter. Like, what do they depend on? So, that's our estimation, right? That's something that we have to estimate. So, I have another distribution. If I was to look at something called an exponential distribution, an exponential distribution is basically a distribution which sort of measures the time it takes between two events. So if let's say I am again standing in that same bus stand, but this time instead of counting the number of buses going in a given interval, I start looking at is how much time exists between two buses that come by. So the first bus comes, and then the second bus comes, and I measure the time between them. And the second and the third bus comes, I measure the time between them, and so on. And if I start looking at that times, not the count of buses, then what I have is an exponential distribution. And that's also dependent on another parameter called alpha, which is obviously the average value of what the exponential distribution looks like. Now, I'm not describing these distributions, and it's sort of like I'm assuming that you all already know. Again, machine learning practitioners are not conversant with distributions, and statisticians would be more. But I would again encourage you all to really go down that road and familiarize yourself a little with distributions, because this is where a lot of probability sampling is going to happen. At some level, you have to have an idea of like, okay, if I have to model reality, what kind of distributions I should be modeling them on. So I have now made those suppositions. Once again, count depends as a Poisson of lambda. There are two lambdas, one before a particular day tau and one after a particular day tau. Then I have two, each of those lambdas depending on an exponential distribution, and the exponential distribution has the same parameter. And this will require another explanation, like why should they have the same parameter? Why not different parameters? But I'm going to skip that. And then tau is basically because there's 70 days or 75 days. I think it's 70 days. I think that the chances of any particular day being the day of behavior change is equal. So I model it as a discrete uniform variable. And then I go into pi MC3 and use that as a way to describe my model. So I describe it as like with pm.model as model. All this is saying is so that it puts into the context of a PyMC model, which is just a Pythonic way of writing something. I say alpha is 1 upon count data mean. Now this is what this alpha is, this alpha here. And because it was time between two events, if I look at the average number of counts, then that gives me an average time between two intervals, right? If you remember, if you have to convert between time and counts or frequency, you sort of write frequency as 1 upon time or time as 1 upon frequency. Here I'm taking the frequency to be the mean, and so 1 upon frequency gives me time, and that's what the alpha is. Lambda is an exponential distribution. Lambda 2 is an exponential distribution. Tau is a PM discrete uniform. Then I go ahead and I create what is called a switch point. These are ideas which exist. If you were to read PyMC and solve Bayesian, a switch point is, a point where, just like I described here, this is a switch point. Like a switch point, which is coding like, okay, a different value for before tau and after value before after tau. So that's what I'm coding here. I'm saying, if tau is greater than a certain index, and here index can take any value between 1 to 70, then, it's lambda 1, otherwise it's lambda 2. And then I actually fit my model. So I say, okay, my observation is basically that there is lambda, and the lambda was described as a switch statement, and then the observed is actually the count data. And then we let PyMC do its magic. PyMC goes, it takes all these distributions and it goes and creates random samples and a whole bunch of posterior, and then it'll sample from that and create and come up with a bunch of samples to me, just like I did in the circle square thing. So once I have done that, I'm using an algorithm called Metropolis here to step through this, and then I ask for PyMC to give me the samples, and I'm asking for 10,000 samples. Based on that, I whatever samples the trace value can calculate, because there are three different things that are being computed. It comes back with three different samples. I index the dictionaries and I get the samples for lambda 1, lambda 2, and the tau, and then I plot them. And here is what the plot functions looks like. It sort of draws a histogram. It says that there is a mean value for lambda 1, which is maybe close to something like 18, the mean value of lambda 2, which is close to maybe around 22.5 or something. And if I look at the tau value, then the tau on the 41st day, there is some probability that there is change in behavior on the 42nd day, on the 43rd day, which is higher, and on the 44th day, which is the highest. Obviously, the behavior change couldn't have happened on a day. Perhaps it could also happen on a given day, but in this case, it's there is 4 days over which the behavior changes happened. And when I try and plot all that, this is what lambda 1 is representing, around 18. This is what lambda 2 is representing, and there are at least 3 to 4 days over which the behavior change happens. Now I have a quantified way of looking at what's going on, and I can answer that question that was asked of me, is like, has the behavior changed? Uh, what days did it change? And what has the change been about? And so a problem like that can be solved very interestingly using some sort of a Bayesian approach, which is which is sort of interesting, because it's not, again, a problem like that. If you want to try and solve it using machine learning, be my guest. I mean, it's just not so obvious how one would use machine learning to solve a problem like that. It's still possible, I'm guessing, but Bayesian tool, a Bayesian approach can actually help solve that problem very, very quickly. So that's that. I have one more example to show you all in a Jupyter notebook, just to make it slightly bit more, um, tangible, to show it. I wish I could show it in action, but I wouldn't. It's easier perhaps to show using just code. I don't want to run it because it takes time, and that would just take away from the time that I'm spending here to show, to describe what I'm describing. So here is basically a problem. The problem is that, let's say you're an astronomer and you point your telescope to some planet and you make certain observations of color, and then using that, you want to infer whether there is water or there is not water. So let's say that's what you're trying to do. So I have 5 observations. I have an observation of 0, 0, 1, 0, 1. Let's say 0 represents a color which is not indicative of water, and 1 represents a color which is indicative of water. So I have 5 observations, 3 of them no water, 2 of them of water. So water observations is basically 2, and total observations is 5. Then now my question is, the question I'm asking is, what are the chances of water being there on the planet? So I set up a prior. The prior is that, okay, the chances of water being present on the planet is any number with an equal probability between 0 and 1. So I set it up as a uniform prior. Then I have to calculate a likelihood, which means that I need to be able to say what are the chances of this evidence being visible, given that the data, the hypothesis is that there is a certain amount of um, that the hypothesis is true. What are the chances that I'll see this evidence? Right. That's what the likelihood is. So now, because I have 5 observations, I want to say, okay, given 5 observations, what are the chances that I would say that I have water there or not? So if you all remember what's a binomial distribution, it sort of depends on a Bernoulli distribution where you have 0 and 1. A binomial distribution will give you all the combinations of what are the chances of if you had 2 instances where you had something and 3 instances where you didn't have something, what would be the chance of that? And you add it across all of those instances to get the binomial distribution. So the chances of water being present is a binomial distribution with the probability of water, total observations, and the actual observed is water observations. It runs a Monte Carlo. It actually does an inferencing step. It runs all the scenarios of what is going on. Let me pause here and describe this little inferencing a little bit more. So, and this is also going to highlight the difference between what is called frequent statistics and Bayesian statistics. So let's say I want to talk about how many times does a plane accident happen? What are the chances, or rather, let me start from there. Like, you're catching a flight and somebody's really a nervous flyer and he says, what are the chances of a plane crashing? You are a thinker, so you come up with an answer saying, hey, listen, one way to answer that question is if I look at how many crashes have happened across a total number of plane flights that have happened. And so if there have been like whatever n number of crashes over like a gazillion number of plane flights that have happened, then the probability of a plane crash is just that. Now you can say that because there is so many flights that have happened and so many accidents that have happened. But let's say I ask you a different question. I ask you, what are the chances of a person who's, let's say there's a new person, a new politician who's just joined, who's just launched a party, and they are standing for election, and then I ask you, what are the chances of that person winning the election? Now, you can't run a similar thing like you're running for airplanes, like, oh, this person has run for election so many times, so and he's won so many times, so the chances of him winning this time is this on this. You can't answer it that way. How would you creatively answer it? One way you would creatively answer it is you would create what is called alternative scenarios. You would say, oh, I would run a simulation where what if the probabilities, if the probability is this, how many times does this person win? What happens in those scenarios? What happens in with a slightly different probability? What happens with a slightly different probability? What you're trying to do is you're creating a multiple scenarios or alternatives, and then you compute over those multiple alternatives, and that's what where you're inferencing from. So it's typically that's the inferencing step in Bayesian modeling. When we're doing is we are generating a lot of samples, and then we are calculating, and then we're taking a few of those samples and then doing estimation on that to try and say where does that fall and what probability that comes by. So I take a sample of 5,000, and then it goes and runs a whole bunch of algorithms. And this is why today probabilistic programming has become really possible, is because we did not really know how to run these very complex algorithms very, very efficiently. The Markov chain Monte Carlo uh, calculation was first discovered by Jan von Neumann, who's one of the pretty amazing mathematicians that the world has ever produced, and it was done at the time of the atom bomb, uh, you know, the Trinity bomb project, when they were trying to build this bomb, and the calculations they had to be terrific amounts of calculations that had to be done. And then scientists were struggling to figure out how to compute some of these really hard problems without having the necessary theory. And they wanted to use different computation approaches to be able to solve a problem. And so Markov chain Monte Carlo comes from that kind of idea. But to implement it at large scales required very powerful computation engines. Again, something that has gotten facilitated in the recent times, just like machine learning. The availability of GPUs and very good computation infrastructure has played a very pivotal role in being able to create such algorithms. So we run that simulation. We can make that estimation, and then we say what's the probability of water being found on the planet given these facts. And not only that, but what is also being provided, if you see, is what are called confidence intervals. This is another important thing why I like to use Bayesian approaches, is because it gives me not only an answer of a mean, but it tells me how much is my confidence in that mean. And so when I'm going to take a bet, I just don't want a point estimate, but I want an estimate with a confidence interval so that I can be very sure about what's my strength in my belief that I'm talking. So it says that the mean is 0.43, and but here is the interval between 0.12 and 0.75, which is a 94% confidence interval. You can change that to 100 observations. So what I did is I changed the number of observations, the observation type also, and the numbers to a larger number, and I ran that again. And when I did that, I saw my probability increase more, partly because I had more water observations, but partly you can see one clear thing is that the breadth of this graph, the confidence interval, is way wider than the breadth of this. And this is where things are becoming much more solid. I am more precisely and with more confidence able to give a more accurate estimate than oh, anything is possible between 0 and 1, and anything. I'm in the first case, I'm saying 94% probability between a value between 0.12 and 0.75. It's a pretty big range, and the mean can be anywhere here. And so the chances of water being here is also pretty high, here also pretty high. The more narrower you want to make, the more confident you are of what you think things are going to be. And that's happening because I have 100 observations. Not just the fact that I actually have more than one water observation, but also because of the fact that I have 100 observations. So that's where it's coming from. I also ran it with no observations and asked that question, and it said, well, in this case, the prior is there is a chance that you will see some, well, chances of it being there, that there is water, but it's really really low, some number like 2.205, 0.38. This was just me pushing the experiment a little here and there. But hopefully, you all get the idea around the important things that I wanted all to understand is that when it comes to inferencing, there's a whole bunch of things that are going there. One needs to think through inferencing as an activity. Before that, you need to be able to build your model sensibly. That requires thinking, working with probability distributions, thinking about what kinds of logic would be the best way to model those scenarios. And then, of course, behind that is this whole idea of being able to come up with different hypotheses and explanations. That's the big idea in Bayesian thinking. Bayesian thinking is also about, at some level, being able to talk about what is the degree of belief that a person has in what they are saying, as opposed to it being very very objective. So it's something sometimes also referred to as a subjective belief system. All those are different ways Bayesian thinking is expressed and used. Finally, to close my talk, I would just reiterate once again that the data scientist has multiple tools in their toolbox. I would really encourage you all to have some thinking tools which can make your working with domains a lot more easier, and a lot of that would come from Bayesian, can potentially come from Bayesian reasoning, modeling, and inferencing. So that's that. I would stop my share at this point, and perhaps take questions in case you have any. I'm trying to look for questions here and see if there's anything that can be.
Hey Anurag. Hi Anurag.
Hey, and hi.
So I will read out some of the questions for you.
Sure.
So there's a question which says that will our prior understanding of mathematics also will define what kind of hypothesis we make uh, for some of the approaches and modeling.
So to be able to build a hypothesis, you need two things. You need the knowledge of the domain that you're going to that where the problem is coming from, and then you need some amount of mathematics to translate that hypothesis into mathematical symbolism. So, for example, let's say I want to solve a problem in healthcare. I need to know what could be various hypotheses that could explain an observation. So let's say I'm looking at a tissue scan, and the tissue scan is colored in some manner, like I see some cells which should not be there. Now, for me to be able to explain that observation, I would need some knowledge of biology or medicine or healthcare to be able to make that. So that's the first thing. And then I want to represent that as a probability distribution or as some kind of a mathematical construct that I can use in my framework and model building. And so both of them are necessary for me to be able to do something like that. So you need both. You need domain knowledge and you need some amount of mathematics to be able to represent that.
And pertaining to the hypothesis which you walked around in the workshop, there's a question: do we need to have a prior knowledge of UFOs and aliens for this hypothesis?
You need an explanation. So you see, you definitely need to let's think about a person, a child who has never seen a movie on UFOs and aliens, and let's say that child is shown this. He or she is sitting at the window and they see a brightly lit object. They might not be surprised by it because their worldview or experience of this world is not complete. They are looking at everything with fanciful eyes. They look at even a tree with surprise. So when they see a flying saucer, they see it with the same surprise that they look at a tree. But for a person like yourself, who's let's say 30 years of age, has had a good exposure to how life is on planet, you've seen enough movies, you would know that your experience on Earth does not account for flying saucers, and you have some view of that, oh, such a thing could come from something like this, like from an alien race, which is where the domain comes in. So everybody who has lived on this planet and is aware of science a little bit and has watched Star Wars or Star Trek is aware of aliens and aware of flying spaceships and so forth. So you are going to use that domain knowledge to sort of come up with a hypothesis saying it's a UFO. So what do you have? You have domain knowledge, like I said first. You don't specifically have the hypothesis. You take that and then you formulate it.
Okay. Another question which we are getting from a lot of people is, can you recommend some of the books, videos to be referred to get more understanding of Bayesian approach?
I would recommend one First of all, one resource that I can recommend is go to the PyMC website, and it has a whole bunch of links to videos and tutorials. So that's one good place to start from. If you are looking at, um, you know, mm, a deeper dive into the into a step-by-step procedure of how to do this, then the Camps Davidson book, which is also linked on that website, is an excellent resource. It's a digital book. It's for free. You don't have to pay for it, and you'll just get it off on that website. So those are the two resources I would recommend.
Another question which we have is, can you quickly tell more about naive-based classifier?
Sorry, what based classifier?
Naive-based classifier.
I don't know what that word is. Naive. How the naive base? Acha, okay, naive base classifier is an NAIVE. Okay,
Yes, yes.
naive base classifier is very different. See, it's a frequentist approach. A naive base classifier is a machine learning approach to be able to make predictions. This has nothing to do with Bayesian reasoning. And I think I'm going to take that question in the spirit that what's the difference between Bayesian approach that I just talked about and the naive Bayes classifier? So the naive Bayes classifier is a machine learning approach to predicting a certain outcome, especially in a multinomial or a binomial situation. A Bayesian approach is to solve a problem where you're not just dependent on um, uh, a point estimate, but you're interested in coming up with a confidence interval. You want to preserve your uncertainty, and you want to solve a problem that way. So two different things.
Okay. Another question is, the prior experience indicated here is supposedly gained from the sci-fi fictional movies. Can it be a reliable factor in this probability calculation? This is more pertaining to the model which you showed.
Yeah. So priors are, if you look about what priors are probability distributions. They are not, uh, they are not subjective things. What am I using as a subjective thing? I'm using my domain knowledge as a subjective thing. The fact that there are aliens, that's domain knowledge. So that knowledge is important, which is why I said when you want to formulate hypotheses, you have to know domains. The one thing that you're using is your prior, not your prior experience, but your prior exposure to the domain of aliens. And so that's what you're using to come up with a hypothesis. But the step around converting that into a mathematical statement is still important, something that you have to do.
Okay. Another question we have is, do you think that Bayesian statistics has the power to replace frequentists?
They are two different approaches. I'm not sure about replacing any of them. They're both tools, and they both have different purposes. I use Bayesian approach to solve certain problems. I use frequentist approach to solve certain problems. Wherever I have enough data where I can do some point estimate, and the goal is not to preserve uncertainty, I can just use a frequentist estimate. But sometimes the problems are very different, and there I use a Bayesian estimate.
Understood.
So different tools for different things, and you want to have a multiplicity of those tools.
Okay. Another question that is come a lot frequently in the chat is, what are some of the practical use cases? Can you also talk about some of the practical use cases where Bayesian statistics plays an important role?
So think about, let's say a company is running an ad campaign, and they want to know how many people are positively impacted by ads versus how many people are not positively impacted by ads. Um, a problem like that can be solved with Bayesian reasoning very, very simply. If I want to solve a linear regression problem where I see a relationship between two variables, but at the same time, I'm not very sure about how confident is my linear regression, I can use Bayesian approaches. Um, Practically all problems where I am doing any kind of inferencing could be solved using Bayesian approach. So whether it's marketing and sales, whether it's healthcare, whether it is supply chain, and so forth. You have to formulate the problem, and the problem has to be formulated in the way that I just described in the example. For example, right? Let's look at both those use cases, and that can help you generalize. I am making some observations about a planet, and I want to make a conclusion about is there water or not. Now, such a question can be answered. So I can make observations about anything. I can make observations about patients. I can make observations about customers. I can make observations about bugs in a piece of code, and then I can try and answer that question, right? So all those scenarios would be practical use cases. It amounts to, can you frame the problem in such a manner that Bayesian statistics can help?
Another question that has come up is if a resource knows statistics to a resource who knows statistics to explore more in applying it, what languages or software needs to be learned?
You if you can choose one language, you can choose one language like PyMC3 or Stan or TensorFlow probability. See, I languages are not problem. The problem is how nicely can you use a tool to solve a problem. Frankly, a lot of data scientists and machine learning engineers get too obsessed about PyTorch or TensorFlow or Stan or PyMC3. You should stick with one language, really master it, and be able to use it to solve a problem as efficiently as possible. The goal is problem solving, not learning multiple languages. So I, for example, know Python, and I know PyMC3, and I'm content with that. I don't want to do 10 other things. I would suggest a similar approach to most people, that figure out what language works best. Of course, there are, not all languages are equal. Some are more powerful than others, and you have to look at things like communities and the quality of people who are working on the on and build on and maintaining that repo and so on. So you have to keep that in mind. But I would say that stick with one or two, at most two. One is sufficient, actually. And then use that as a way to solve the problems.
Understood. Maybe last question we'll take. How can one build a career in data science or machine learning? Is there a self assessment available to measure one's readiness?
I'm not sure if I know about the self-assessment things. You can go and do Google searches on that. But I would recommend taking, if you're serious about data science and machine learning, take a formal course on data science and machine learning. Invest your time and energy to really build and learn it from first principles in a structured program. That's one way to get exposed to something. Of course, if you're a very powerful self learner, you can gather all the resources from the web and make yourself a program, but that's just harder to do. Sometimes it's easier to just follow a structured program that somebody else has designed and then just try and finish it, rather than just cursorily do it. In my mind, that's a better way to build a career in the area of data science and machine learning.
So another question that has come up is it is how do you decide the length of sequence that was duplicated in Bayesian method? And a lot of people are saying that they find it difficult. So any take on that?
Sorry, I didn't get that question completely, Amita. Could you repeat that, please?
How do you define how do you decide the length of sequence that was duplicated?
The length of sequence that was duplicated. I'm guessing that they are talking about the water observation problem that I described. Is that right?
Yes, yes.
Yeah, I just took that as a so I guess the more important question is, how many observations do you want to have to ideally be able to solve a problem properly? Now, that is not something you can decide. While there are some ideas around how many observations you should have, you are given data, and then you have to make the best estimate from the data. So whatever data is given, you make the best estimate from that, and your confidence interval comes from that. If you have the luxury of designing how many observations, and I would say as many as possible, because more you have, the more narrower your um, precision is going to be, about the confidence interval. But otherwise, you just have to deal with whatever you have.
Another question is, according to you, what are some of the disadvantages of using Bayesian approach for your model?
Disadvantages. That's a good, interesting questions. What could be one disadvantage? Frankly, that's a hard question. I don't know the disadvantages yet. Um, well, frankly, I don't know how to answer that. I mean, I can't think of a disadvantage.
Okay, no worries. So I'll just ask a last question before we head out for another session. Scrolling. Uh, so also there has been a discussion on chat around scoring metrics and designated gap penalties. So they're also asking what are some of the methods to align a pair of sequence for Bayesian approach.
I am not sure where that question is coming from. Align a pair of sequence. What is that referring to? I actually don't know what that is referring to.
No worries. I,
Uh,
I think a lot of discussions happened over chat, and when you were talking, people were posting a lot of things. We have got very good comments from attendees in terms of the length and depth and the breadth you covered. So thank you so much for that. Really appreciate it. Thank you for joining us, Anurag. Now we'll move to our next workshop for the day. Thank you,
Thank you.
Anurag. So I hope this session was useful for everyone.